This is a production of Cornell University.
This brings us to these two questions. Okay, and the first question is, well, if I'm talking about all these ions that are in solution, where in fact are they coming from? Okay, now this is not just the ions that are going into isomorphic substitution, but these are the ions that are actually exchanging on these exchange sites that we're producing because of the charged molecules, or colloids. Okay, and then the question is, and this goes to Kata's question earlier, can you give me some examples of some of these ions? Well, which of these ions in fact do bind to these exchange sites? Okay, so if I have a negatively charged particle, I'm definitely not going to be too attractive to other negatively charged particles that are in the soil solution. The ions, I should say. Does that make sense? But I will be attracted to positively charged ones. So let's start with the first one. Almost all the ions or molecules that are in the soil are either sorbed by the roots in the long run, are either sorbed by the roots, they're taken up into the plants, or they're leached away. Those are the two things that are going to happen to them. Now, in the interim, though, they can be held in the soil by cation exchange capacity, the ability of this soil to hold on to these things. But for these things to be absorbed by the roots or to be leached away, first, the ions themselves must be released into the soil solution. Okay? Now, this can happen because cation exchange, i.e. coming off of and being exchanged onto these colloids, and also anion exchange, the same thing, except this is a positively charged ion and this is a negatively charged ion. Okay? I also can have ligand exchange, and I'll explain what each one of these are in a moment. But ligand exchange is basically you're looking at an ionic or covalent bond that's actually multiply binding to a central ion. So it's a metal usually. Okay? We can also have dissolution precipitation type of reactions where like calcium carbonate, I throw calcium carbonate into acid and it starts to dissolve. And then lastly, I can have something that's called surface chelation, and it's actually it's a ligand bonding type of reaction, but it's a very specific one and it's associated with organic molecules. Okay, so let's start with a cation exchange. Clays have this negative charge that comes from that isomorphic substitution. And organic matter also has this negative charge, and it has to do with the carboxylics. Cations are loosely bonded through sort of electromagnetic attraction to these particles. Okay? These particles, or I should say not the particles, but the ions themselves can exchange. Now, this is not an ionic bond. This is just an you can think of those magnets. I can get them, and it can be really tightly held, but I can still pull them apart. They're not the same object. Okay? So if I put another magnet into the system, a stronger magnet, for example, that magnet could potentially bounce off the first ion that's held and exchange for it. Does that make sense? Okay. So here's my soil colloid. Here's a calcium that's being held on to this colloid. I start raising the magnesium concentration in the solution. This magnesium could literally take this calcium and bounce it off, put the calcium in solution, and be replaced by magnesium. Now, there's reasons why this is important, and you guys, off the top of your heads, you probably can think of it right now as a sort of soil fertility. But remember me saying there's really only two places these ions are ultimately going to go. They're either going to go into the plant roots or they're going to be leached from the system. So why is this cation exchange capacity so important? Well, this exchange complex holds on to these ions until the plants are ready for them. Okay? If I throw a lot of fertilizer on and the plants can't take it up, where's that fertilizer going to go? It's going to be leached right out of the system. The second option for this material. As a result, these exchangeable ions are not leached from the system, but they are not leached away from the roots, in essence. Okay, so if I have a volume of soil, okay, and here are my roots in this soil volume, and this soil volume is holding on to these materials, okay, they're going to prevent that stuff from being leached away, and they're going to keep it in the proximity of the roots. Does that make sense? Okay, which I just heard my phone, which means I forgot to turn it off. Sorry. The other cool thing about this, remember, because these things can be exchanged, these ions, when the plants start wanting them or need them, are rapidly exchangeable. Okay, the plants literally have the ability to start pushing ions out into soil solution. Those ions then compete for the exchange sites. They release the ions that are on those exchange sites, put it into the soil solution, and the plant can then harvest it. Many more cations reside on the exchange complex than in the solution. Okay, so if you think about this soil solution here, here's the soil solution, and here's the colloid. There are a lot more of these ions that are sorbed onto the exchange sites on the colloid than are in the soil solution. And that's a good thing, because if they're out here and they're not being taken up by the plants, they are being leached. They're moving with that water. And lastly, and this is sort of more, you guys know that I'm interested in heavy metals and things like that, not the bands, but this type of ion exchange can actually purify a metal polluted water or soil. Okay, it's not going to purify the soil, but it will purify the water that in fact has the contaminants in it. You run the water through the system, the water brings in the contaminants, the soil then basically binds, because all these metals are ions and they're charged, and soils in essence the charged particles can then be attracted to the colloids. Go.
No, I was just thinking about the lead in Dillman Farm. So as you add the compost to it, will you eventually bury it and it'll be part of that whatever process, and that would?
Yeah, so the question was, if you keep adding organic matter, so in Dillman, remember Dillman having the lead arsenate. If you keep adding organic matter to Dillman Hill, will you in essence bury that material? In a sense you will, but in a sense you won't, because that organic matter is being decomposed. Okay, so as I bring more organic matter in, I'm certainly increasing to a certain extent the organic matter composition of those soils, but I'm going to get to a point where decomposition rates are going to be just as fast as accumulation rates, at which point I'm sort of have stabilized my organic matter. Okay, the organic matter will in fact also, and we'll talk about this when we talk about chelation, but the organic matter also will bind these heavy metals in addition to the colloids sorbing them. Okay, but let's hold off on that one when I start talking about chelation. Okay, go, question. True if the metals were soluble in them.
Well, and it would be pH dependent.
It would be pH dependent, and so the question is, this would only work for certain scenarios, because metals are more or less soluble in water based on the pH, and the lower the pH, the more lead, for example, is soluble. Okay, so if I have a low pH material, I'm going to have soluble lead that's going to move into these soils. But if the pHs were neutral, in all likelihood, the lead is not going to be moving with the water because it's not soluble. And that's one of the benefits at Dillman Hill, for example. The reason those leads the lead is staying in the soil is twofold. One is I've got clays in there that have good cation exchange capacity, but two, the water that's moving through the system is not very acidic, and so as a result, the metal, the lead, is not soluble, which means it's not leaving the system through leaching. Does that make sense? Okay. All right. So, cation exchange, what in fact controls this ion exchange? Okay, it's important. We got 5 nice reasons here why it's important, but actually what is actually controlling that exchange? An exchange is basically controlled by 4 things. Here's the first three. The first one is cation selectivity. It turns out if you think about those magnets, the larger the magnet, with the same charge, the larger the magnet, the tighter it's going to be held by the soil. Okay, by my other magnet, okay? So here we have a potassium versus a lithium. Okay? The potassium, because of its larger shells, is less likely to be exchanged than the lithium. Now why? You got to think about the nature of these ions. Here's my colloid, whatever it happens to be, negative charge. All right? Here are two different cations. Okay? The positive charge is sitting right in the center. The negative charge is in the orbitals around it. Okay? So for this to be knocked out, for these ions to be knocked off of this surface, the positive charge has to be knocked off. The distance here between here and here versus here and here is significant. So as a result, it's harder for that positive charge to get in here to knock that out. It's a lot easier, if you look at that, for the lithium to be surrounded by protons, by water in essence, than the potassium. So the potassium, because it has a larger shell, it's more likely to hang on to those exchange sites. So the first rule is basically size. The bigger it is, the tighter it's held. The next one is the charge equivalence. And this totally makes sense. The higher the charge, the tighter it's going to be held. So if I have a +1 charge versus a +2 charge versus a +3 charge cation, the +3 charge cation is going to be more likely to knock somebody out and more likely to be held to stay on the exchange sites. Does that make sense? Okay. The third is the ratio law. This is basically, for lack of a better rule, we actually really more call this the mass action rule. But the more of one ion I have over another ion, the more likely that first ion is going to be in the exchange sites. Think about my soccer analogy way back. Okay? I have one really good soccer player and one really bad defender. Okay? In all likelihood, that soccer player is the offensive player is going, not offensive. The attacker is going to score the goal. But then what happens when I start putting 2 defenders on them? And then 3 defenders, and 4, and 5, and 6. Sooner or later, that mass, just the sheer mass of ions is going to be able to knock out that other ion. Okay? For gamers, this is like a good analogy would be a Zerg attack. Does this mean anything to anybody? Okay. Basically, you just throw enough things at somebody, and sooner or later, you're going to win. Bear with me. All right, so we got cation selectivity, we got charge equivalence, and we have the ratio law. Okay? The last one is what we call complementary cations. And complementary cations is basically, it's sort of a combination of all these things, but you have to imagine, let's use this board over here. Here's my charged surface, okay? And my soil solution is up here. This is the soil solution. And on this charged surface, I'm going to have a lot of different ions that are being held. Okay? Now, if on this charged surface I have something that's being held really tightly, let's imagine this is a +3, and this is a +2. Okay, actually, make this a little bit. Oh, okay, +3 and a +2. Just use those two. In all likelihood, which one of those is going to be the one that gets bounced off? The 2. It's smaller than this, and it's got a less charge. Right? Okay, how about this, though? Plus. Which one's going to be more likely to be held there? This guy. This has got the charge benefit, right? It's got the same shells as these guys, but it's got a higher charge. Okay, which means when things come in to compete here, it's more likely to pop this guy off than this guy off. And it's more likely to pop this guy off. This guy over here is sitting pretty. So it's the combination of the ions that are on the site that are also going to contribute to what's going to get popped off, what's going to be exchanged. Does that make sense? Question.
Which is more important, the size of the cation or
if I had a bigger +2 here, take this and turn this into a bigger +2. Which one? This one versus this one? Which is more likely to get knocked off?
Like that. So the big +2 and the small +3. Which one will survive? Which one?
Oh, okay, now I understand what you're saying. I actually don't know. I think it's going to have a lot to do with what's out here as well. Okay? But the reality is this is a combination of all these 4 factors that are going to be controlling this. Okay? The size, the charge, the number, and its arrangement next to whatever it's next to. Okay? So in this case, this guy is probably going to get kicked out first. I mean, we're looking at all of these at the same time. It's not like we're just picking on this guy. We're looking at the exchange. These guys want to exchange with all of these guys. They want a spot at the table or at the colloid. Okay, so in all likelihood, this is the one that's going to get knocked out first. You know, these guys are probably, I'm not quite sure. I think it'll have depend on what shell this actually is. You know, but I'm thinking that, you know, it's probably a little bit of both. You know, and then on top of that, if there's a lot of these +3s out here, you know, if you start thinking about the mass action rule, okay, this one might be the one that gets knocked off, but it's going to get replaced with the same thing. Okay, so it's a combination of all 4 of these that are controlling that cation exchange. Go.
I'm a little confused about the first one. If you have a really big cation and you have lots of, you know, negative shells, wouldn't that make it more weakly held because the positive charge is greater?
You would think so, but what happens is it's not like. Here, let's use this one. It's not like the ion is sitting like this. The ion is actually sitting like this, with the positive here and the electrons out here. Which means if I have an ion that's out here that wants to exchange for this guy, it's basically the entire body has to get inside this to knock it out, because it has to go through all of these electron orbitals as well. Okay, now granted, these orbitals are going all over the place, so as it gets closer and closer and closer, the electrons are going to be more concentrated on this side of it. But this is happening really, really fast. You know, so as this thing is moving in, you know, it's got a bigger force field. You know, what am I trying? How do I explain this in a different way? It's this that's being attracted to this. Okay. Now these ions that are in here, they're positively charged, but they still have these electrons. They still have some negative orbitals going around them. Okay. So they need to get that positive close to this, and if this is in the way, the distance that they're going to be attracted is this far, versus one that's like this, it's only going to be this far. Does that make sense? Yeah? Another way to think about it is sort of these magnets coming closer and closer together. You notice how you get closer and closer together towards the other magnet. It gets harder, it gets stronger and stronger and stronger. Well, this magnet is just being held, is preventing everybody else from getting very close, so it's not attracted as much. Does that make sense? Yeah? Okay. Go.
So since some ions are held tighter, is there sort of like an eventual equilibrium that happens at all, or is it just?
That's a good question. So the question is, if some of these ions are held more tightly than others, do I in fact ultimately reach an equilibrium? And as long as I don't change, so let's go back to this drawing. So if we imagine I have an entire soil, okay, and in a little part of that soil we're looking at this colloid coming out here, right? Okay, so the solid is here, a negative charge, net negative charge. And this is all soil solution out here. This is a pores. Now there's another colloid over here and so on and so forth, right? Okay. Depending upon what the concentration is out here, I'm going to get into an equilibrium. But you have to imagine what's going on in this entire soil. Okay. As things get pulled out of equilibrium and into this location, I'm changing the concentration gradients around here. And so other things are going to start moving into this. And so there's going to be so you can sort of say, okay, potentially I could reach a dynamic equilibrium. But we are operating on a terrestrial system, so there is always some sort of event coming in, a rainstorm. It starts to rain, it's going to be bringing in more protons because rainwater is naturally acidic. So I'm going to be changing the proton concentration. Okay? As the organic matter up here decomposes, I'm going to be putting more ions into solution. So I'm changing this dynamic, this soil solution. And as long as I'm changing that solution, this is going to be dynamic. I fertilize. You can think of a lot of different scenarios. Now, yes, we have a closed system. We certainly can create this dynamic equilibrium where we basically have X amount of something here and X amount of something out here. Okay? But even in that scenario, these guys, calcium here is exchanging with calcium out here. It's not like these guys stay in solution and these guys stay here. Does that make sense? Okay, question.
So in the example of the heavy metals in a clay soil, if you put organic material on top of that and you have acidic rains, would that mean that the metal is held less tightly?
The question is, this is sort of, in a sense, kind of a remediation technique. Okay, if I have a clay soils like the not like the Hudson soils, okay, and it's holding on to lead, okay, what happens if I put organic matter on the surface? Well, I think that I wouldn't probably put the organic matter on the surface. I'd probably put it down below around here or integrate it in, because with the rain system and I start raising the pH or lowering the pH, I mean, let's talk about lead, we want to lower the pH. The system is going to be driving stuff this way. It's not going to be driving it back up towards the organic matter. So if I wanted to use the organic matter to hold on to these metals, I'd probably want to put it into a better intimate contact with the contaminated material. In the system here, around here, the water flow dynamics is this way. Now, yes, there is some water flow dynamics this way because of root uptake, okay, but most of it is going this way. Now, if I was starting to think about something out west where it's a drier environment, and I start looking at this kind of mobility, capillary action moving things up, maybe that might be a scenario. But from a remediation sense, I'm not actually remediating, I'm just moving. I'm moving it into the organic matter. But I would really have to lower that pH to be able to do that. Does that make sense to everybody? Does everybody understand the premise? Okay. You cool? And this is all this cation exchange is all possible due to the charged nature of these molecules.
This has been a production of Cornell University, on the web at cornell.edu.